Why don't we go ahead and get started? I think we'll finish up the chapter today. It seems like there's an awful lot to talk about, but a lot of it we can kind of condense and just explain what it is that Bushong's trying to get to. So we'll review what we did last time. We talked about electromagnetism, and that's really where, or we're talking about magnetism, and that's, we're going to talk about that today in context of electromagnetism, using electricity or magnets to create, or electricity to create magnetism, and magnetism to create electricity. So we talked about the magnetism just all by itself. We talked about what a lodestone was, and that's a natural magnet, which is one of our classifications of magnets. We'll talk about that again in a second. We talked about the phenomena of atoms that have unpaired electrons, where we have, he throws a couple of different terms out there: electron spin, creating a magnetic moment, and that's because of unpaired electrons. So in an atom with unpaired electrons, it shows some degree of magnetism. Does not necessarily mean that, whatever it is that is made of unpaired electrons is necessarily going to be magnetic, because of the orientation or randomization inside of the structure or the compound, whatever. But each individual magnet can show some sort of magnetic properties. We'll talk about that in context of how we create an image in MRI. We talked about a magnet being a dipole or bipolar, having two poles, a north pole and a south pole, kind of like the positive and negative charges in an atom. We talked about what a magnetic domain was, and that was where you have a collection of magnetic dipoles or magnetic moments, enough of it that we can get some sort of measurable magnetism off of it. We talked about the classifications of magnets. We got permanent magnets and temporary magnets. Impermanent magnets, we have natural magnet, and we have man-made magnets. And we said that the characteristic of a temporary magnet is that you could stop it, you could turn it off. Exactly. So that's really kind of where we're going to live today, is that we're going to create magnets, pretty much. We're going to use that magnetism to create the energy level that we need. So then we talked about the different types of material. We had non-magnetic, which is just as the name implies, has no recognition of a magnetic field, no reaction to a magnetic field whatsoever. And we talked about diamagnetic materials, and those were weakly repelled. We talked about what a ferromagnetic material was, and that's something like iron that's very strongly attracted to a magnetic field, and we're going to talk about that more today. And we talked about paramagnetic material, which is weakly attracted, and we took a look at what that looked like. Aluminum being very weakly magnetic, to the point that we can't witness it without something as strong as, say, a MRI. And then we talked about the laws of magnification, magnetic laws, magnification, totally different. So we talked about those in context of electricity, and the similarities between laws of magnetism and electricity. And we've got attraction and repulsion. Like charges repel, and unlike charges attract. And then the second one was basically Coulomb's law applied to magnetism, and that was the more magnetic domains you had, the stronger the magnet you had, and the closer you pushed those together, the stronger the magnet you had. So the second half of that, that's really backwards of the way it's stated in Coulomb's law, and that is that that magnetism would be inversely proportional to the square of the distance between them, meaning that if you spread them out, they're not going to be as strong. The magnet's not going to be as strong. So we're going to talk about that more today. So we talked about the minimum amount of magnetism would be, there is none, right? The smallest magnet would be the magnetic force you would find in one electron, but because those electric lines spread out right? Infinitely. There is no minimum unit of magnetism. We talked about magnetic induction. That is, that if you put something magnetic up against something that's ferromagnetic, then you're going to induce a magnetic field in that ferromagnetic material. It also becomes at least temporarily magnetic. Okay, so that's not to be confused with temporary magnets, right? Temporary magnets are, you flip a switch, it's on, you flip a switch, and it's off. And again, we're going to talk about those here in a minute. Roll one with me, a couple of them. Okay, so any questions on all that? No? All right. So then now we're going to talk about electromagnetism and how we're going to use what we talked about last time to accomplish what it is that we need to accomplish. And we're going to have to walk through that in steps to really kind of understand it pretty well. So just a review of the components of electricity that we're going to talk about is voltage. We talked about voltage and it being electric potential. We said that we're going to call it the pushing force behind the electrons, right? And the electrons then would be the things that we're pushing. So we've got voltage being the power behind the electrons, and the electrons being the flow of electrons, or the number of electrons being our current. And we multiply those two together and we get wattage. And we can get electric current from a lot of different places, and we'll talk about that a little bit. We talk about generators and we talk about batteries. And just, you know, the first, before we created generators that could really generate high volumes of, especially alternating current, we could create electric current. You can do this at home if you really wanted to with different, you do some Google searches and YouTube searches. You can create batteries out of food sources of all things. Lemons, you can get electric flow out of lemons, potatoes, certain things. It's very minimal electric flow. But other things that you can get, and I would say that nobody in here except for yours truly has experienced this, but dissimilar metals, if you stack those together, you can actually get electric flow. So back when I was a kid, the three big chewing gum, not bubble gum, but chewing gum, that was double mint, spearmint, and juicy fruit were the three that everybody always had. Every grandma had in the pocket or in the purse. Okay, they were great, we thought, but they were also wrapped. The inside was paper. The inside of the wrapper was paper, but the outside was aluminum foil. Okay, so back in the day, whenever they gave you fillings, they didn't have that sealant that the dentist puts on your teeth when you're a kid now. And toothpaste maybe wasn't as good. I don't know. But we had cavities back in the day. Maybe we just ate too much candy. I don't know. But we had cavities back in the day. And the fillings they put in our teeth were metallic. And so, you're sitting in, a meeting or church or just driving down the road, you're driving grandma crazy. She's going to give you something to try to calm you down. In some cases, that would be some chewing gum. Put this in your mouth, gnaw on that for a while, and maybe you'll settle down some. But she pulls this out of the bottom of her purse. It's been bouncing around in there. Sometimes it's nasty. But you pull it off, and sometimes some of that wrapper stayed on the gum. But you're 6, right? How closely do you inspect things when you're 6 before you pop it in your mouth? You ever seen a 6-year-old? Cram everything in their mouth, right? So you pop this thing in your mouth and you start chewing, and the aluminum foil and the cavities, which were metal, were dissimilar metals, and sooner or later you would chomp down on that and it would hit that metallic filling, and it just sends you almost through the roof of the car, right? Yeah, you're like, oh, that hurts. Yeah, it did. It hurt. So what you were feeling then was an electric jolt because of dissimilar metals piled together. So early batteries were created like that. And you can actually create a battery with zinc and copper. I think if you just stack them individually on a bolt or something like that, you can actually create a small battery. That's what we refer to as a voltaic pile. And it's a source of electromotive force. Okay, so electromotive force, we're going to add that to basically voltage as well. Okay, so electric pile equals battery equals source of electromotive force. But in order to create X-rays, especially with batteries, we needed something more than that. So early batteries, voltaic pile, and then again, remember when Roentgen discovered X-rays, he was just experimenting with electricity to try to figure out what it was. This guy Oersted was kind of experimenting as well. You know what Oersted had in his lab. You know, they said it was an experiment, and sometimes I wonder if it was just a collection of junk that he had laying around, and he happened to notice phenomena and called it an experiment. I don't know. I don't know. I wasn't in his lab at the time, so I don't know. But what he had was a source of electromotive force, which would be, in this case, a battery, so positive and negative charges. And through this, he ran from this, he ran a wire, a straight wire, and he had a switch on it. Okay, so this represents switch. Okay, this is an open switch, meaning no electricity can flow. Remember your laws of electric flow. You have to, you know, to make electric flow, you have to have contact or induction, right? So you have no contact, you got a low voltage battery, no chance of induction here. So what we've got is an open switch meaning the lights are out. Okay. So he also, though, has a compass. And where's the compass point? North. It points north. It points to the magnetic north of the Earth. So what he noticed was, let's say our compass was oriented this way, and our north is here. And whenever he closed the switch, and closing the switch, again, would imply, or would not really imply, but mean that he made contact between two portions of this circuit, and he's got electric flow at this point. Okay? So he's the guy that first came up with the understanding that anytime we have electrons flowing through a wire, we create two things. One is heat, and the other is magnetism, right? So when he closed the switch and completed that circuit, it's still north. What he noticed was his compass would then point at the wire. Okay. Open the switch again. See what happens. My compass broke. This compass would automatically go right back to pointing north. The compass was fine. So what he noticed was that whenever he had electron flow, whenever he completed this circuit and he had electron flow through this whole thing, that created a magnetic field. And it was a strong enough magnetic field that it changed the orientation of his compass. The compass would point at the wire. So now we have proof of what we've been talking about. We've got proof that when we send electrons through a wire, we know we create the heat, we can feel the heat, but we also can now detect that we've also got a magnetic field. Okay, so that was Oersted's experiment or accidental discovery. I don't know. I kind of tend to lean towards the other, towards more of discovery, because why would you have this together? I mean, how does a compass fit into all this? I don't know. But he undoubtedly was smarter than I am, so he very well could have expected that to happen. All right, so you okay with that? Oersted, again, he's the guy that proved what we've been talking about with the charged particle in motion. If you're okay with that, then we're going to skip over the next page. We're going to get back to that here in a second where it talks about solenoid. We're going to get back to that here in a minute. Now, electromagnet, we'll get back to it. So we're going to talk about electromagnetic induction. So going back to our laws of magnetism, all right, so we've got a magnetic field. We know we've got a magnetic field. What were our laws of magnetism? Opposites attract, so we got attraction and repulsion. But the other one was basically Coulomb's law, which had two parts, and that was
The more you have,
the more you have. How much do we have with this one flat wire? Pretty much one of something, right? So what if then we had, and it's not exactly how this goes down, but just for argument's sake, let's say we ran a second flat wire right next to it. It's going to do one of two things. Either the magnetic field, because their opposites are going to bump into each other, or their lights are going to bump into each other and push each other apart, or they're going to combine forces. I've got two. Now how much do I have? Two. Right. So then what if, and I touched on this on Wednesday, so what if instead of doing that, what we do then is to take our wire, and we're going to build on this really bad drawing for the rest of the class period. What if we take our wire and pull it up like that? And we've got positive and negative, we're touching both ends. I take my wire so that now my magnetic fields overlap each other. Now what do I have?
stronger magnetic field.
Much stronger magnetic field, right? I'm gonna make you count those. I got a lot, so I'm gonna have a lot, right? I had one, I had one, I had two, I had two. Now I got a lot, I got a lot, right? So now I got a strong magnetic field. Along comes Michael Faraday, again, a genius. And Michael Faraday says, okay, all right, so I've got an electric field. An electric field created a magnetic field. Can we create an electric field with a magnetic field? Right? We've got electric field creating a magnetic field. Will it work in reverse? So he said, okay, well, let's get rid of the battery. And instead of the battery, we're going to have a meter, let's say a voltmeter, and we're going to measure and see if we can make a magnetic field or make an electric field, electric flow with a magnetic field. Okay, that's a magnet, right? I mean, it's stuck. It's a magnet. And so what he did was he had a coil wire and he had a magnet. And he took the magnet and he moved it over close to the coil wire. And what he saw was that his voltmeter might have been pointing, it might have been an ammeter, I don't know, it doesn't really matter. But it was pointing at zero. But the closer he got with this, almost kind of like a Geiger counter. You know what a Geiger counter is? You've seen movies. It's that thing is, and the closer it gets to a radiation source, the more it growls at them, right? Well, kind of think of it that way. So with it out here, while he's moving it in, this thing starts to move a little bit, and then the closer it gets, the more it moves. Okay, so this is measuring voltage, amperage through this coil of wire. So did he create electricity with a magnetic field? Well, if the needle moved, that would be pretty strong evidence. Okay, so let's say that's not even a voltmeter. Let's say that's a light bulb. It's a light bulb. All right, so he moves it, and the light gets brighter and brighter, and then he stops. Do I still have a magnetic field? Yeah. Magnetic field's still there. But the odd thing is that as soon as the magnet came to a stop, the light went out. So can I create electricity with a magnet? You did. But it's got to be moving, right? So what that implies is, remember your laws of magnetism.
The magnetic field lines reach out from the south end and come back in the north end, right? And they reach out infinitely. So the light got brighter the closer it got, and then whenever it stopped, the light went out. So what that means is those magnetic field lines that are reaching out from that magnet are influencing this coil of wire. And because they're influencing this coil of wire, it's lighting the light up. But as it's moving closer and closer to it, it gets brighter and brighter. But as soon as it comes to a stop, it ends. Okay. So what does the word flux mean to you? Ebb and flow, change, right? So things change. So the key here is that your magnetic field has to be in a state of flux in relationship to a coil of wire. And it doesn't really matter how that flux goes. Okay? It just has to change. That magnetic field has to change. It has to be in a state of flux. So, he can play with it any way he wants to. He can take it and he can move it in and out like that, right? The problem with that is that the further he moves away, the more magnetic field he loses, right? The light's still lit, but now you got a flickering light. It gets bright, it goes dim. It gets bright, it goes dim. It gets bright, it goes dim. Would the magnetic field be in a state of flux if he moved it up and down this way? Absolutely. Absolutely. Is there gonna be still some loss of that magnetic field? Yeah. The answer is yeah. The more it goes down here, those magnetic field lines are gonna have a tendency to reach down. But is it gonna be as bad as pushing it out that way where you lose? I mean, you've lost half of that magnetic field already, right? In a two-dimensional representation, you've lost half of it. In a three-dimensional representation, you've lost probably 80% of it or more. But by moving it up and down this way, or even through the center of it, you're using more of the magnetic field. Still in a state of flux, right? Still in a state of flux. So our light stays lit. We're still creating electricity because the magnetic field lines are state of flux in relationship to the coil of wire, right?
Would it work better if you just shorten how far the magnet moves?
Yes, it would. It would probably be more efficient. And along that same line, what if it didn't move up and down this way at all? What if instead what I did was I took it and I went, what if I spun it? Okay, so this is south end of the magnet, let's say, and magnetic field lines are going this way, right? So they're going through the center of that thing, going up like that, right? But when I flip it around, how are they going to be going? Opposite way, opposite way, right? Is my magnetic field fluctuating? Big time, right? It's going from this way to that way by way of going this way, right? Major fluctuation, major fluctuation. Basically, that's how generators work. Is that you got a coil wire, you got some sort of magnetic field. If you take the top off your lawnmower, crank it up, you can see that happen. You got a magnetic field and coil wire, and that's how that's happening. All right. We're going to do the same thing, but we're going to do it just a little bit differently. All right. So before we get there, though, I want you to take a look at Faraday's law. So Faraday, again, can I create electricity with a magnetic field? And there's four components to Faraday's law. One is first off, the magnitude of the induced electric current. Okay, I'm inducing an electric current. Coil of wire all by itself inherently has no electric current. You got to have something to make the electric current. You got to have a battery, or you got to have that change of magnetic field. So that process of putting the electric current in it is what we call induction. All right, so the magnitude of the induced electric current depends on 4 factors. The strength of magnetic field. Stop there. All right. So how do we get a strong magnetic field?
More electron.
Okay, you're getting a little bit ahead of me, but more magnetic domains creating a stronger magnet, right? But we're going to get there. The velocity of the magnetic field as it moves past the conductor. Okay, so I take a magnet and I move it. Do I get electricity? Yeah. So it stops, right? Then as I move it out, while I move it out, do I get electricity? Yeah, I do, because again, we're fluctuating. So if I do that, that's the only movement I make. And it's wintertime, so it's dark all the time. How much light did you have to read your textbook by? Yeah. Almost none, right? So what if I move it back and forth and keep the motion going back and forth? Then better, right? And then I move it faster. What's going to happen? Better, right? Okay, so the strength of the induced current depends on the strength of the magnetic field. Stronger the magnet, the more induced current. The velocity of the magnetic field is moved past the conductor. The more we move the magnet, the more electricity we're going to create. Number 3, the angle of the conductor to the magnetic field. We'll work that out in your own mind. And then number 4 is the number of turns on the conductor. So if I only have one coil of wire, it's going to be pretty weak, right? So Faraday's original experiment, just with that one loop of wire, he created electricity, but it wasn't very strong. The more he would have coiled that wire up, the stronger, the more electricity he would have created. So we have more wire, now we have more electrons. Okay? Everybody with me so far? Well, this is where it gets sticky. All right. So let's get rid of our magnet. Take a light bulb and change it. Instead of a battery, now we've got a generator. All right, so I'll go generator. Okay, what kind of current do we get out of a generator? AC, right? Alternating current. What are the characteristics of alternating current? It goes back and forth, right? So it goes that way, and then it goes that way, right? So it goes that way, and then it goes that way. When we send electricity through a wire, what do we create? 2 things: heat, magnetic field. Okay, so the heat doesn't play into this yet. It will. Doesn't play into it yet. So so trying to remember how this works. I want to say that the voltage or the current chases the south end of the magnet. Okay. I may have that completely backwards. It doesn't matter. Okay. So if you look it up and you say, no, it chases the north end of the magnet, it doesn't matter. It doesn't matter. Okay. But this does. So if our electricity is going in, and let's say this is creating a magnetic field where this is the south end of the magnet, okay? Well, it creates magnetic field. Current's going this way is creating south end. The magnetic field that it induces is creating this as the south end of the magnet. What that means is the magnetic field lines are coming out this way. Okay, so the inside of the magnetic field is trying to set up a situation where it opposes the action of the electrons. All right. So if electrons are trying to go in this way, then the magnetic field is trying to come out that way. Okay. So all of that doesn't matter that much until we consider this. If the electricity, and that's a big if the electricity chases the south end of the magnet, what happens when the electricity now, instead of going that way, is going this way? Now it's going this way. It's going to happen. Magnetic field switches. Okay? So now the south end of the magnet is here. Okay, following? So what does that mean in context of what we just looked at?
Switch all the time.
It switches all the time. How often does it change here in the United States? 60 times per second. So somewhere in between. It's 60 hertz. 60 hertz means 60 times per second. That phenomenon happens where the electricity goes in and comes out, goes in and comes out, goes in and comes out. Okay? Which means that your magnetic field flips 60 times per second. Okay, what is that creating that we just talked about?
A lot of electricity.
A lot of electricity creating a lot of heat. Something else in context of magnetism. What does it create? The magnetic field, but the magnetic field is always changing. Always changing. It's always changing, right? So not only do we create a magnetic field, but we created a magnetic field in a constant state of flux, right? So now, what if we came along and I put another coil wire right across from it? What could I induce in this coil wire because of the changing magnetic field in that one?
Electricity.
Electricity.
Whoa.
Right.
Okay.
Yeah,
That's
crazy, huh? So we send a lot of electricity through this to create a very strong magnetic field, or to create a strong current that creates a very strong magnetic field that's always in flux. So we can put another coil wire here to induce electric current in it. Okay? So I'm going to pass around this. This is a filament transformer. And what you'll see, you got to look at it kind of close, but what you'll see, there's two coils of wire in here. Okay? So if you look at it close, what you'll see is one coil of wire is pretty small. Okay? The wire itself is pretty small. The coils are identical in size, but the wire is pretty small. So if we have a skinny wire occupying the same space as a fatter wire, then what could you say about the skinny wire and the number of turns on that skinny wire? It's about a bit more, right? So we're going to use this to make a change in our current in our filament circuit. Okay, so I'm gonna pass this around. It's got a little bit of weight to it, so don't drop it on yourself. Okay, so let me back up to a single coil just for a minute. All right, so I got a single coil wire. Whenever you have that flipping around of things, going one direction to the other, you're gonna have some delays. It's 60 times per second, so it's not gonna be significant delay, but I take this strap, I spin it around like this. Does it ever stop? No, let's not stop it. But if I do this, does it? It stops a little bit on each end, if only for a second, right? If not even a second, just for a split second. So might there be some hesitation between the magnetic field as it switches around? And the answer is yes. It's insignificant. We're going to talk about that in context of transformer loss here in just a second, but it's insignificant. What we get in a coil wire is that we do have some loss. It's not 100% efficient. It's efficient enough that we have what we call transformer laws. And a law in mathematics means, in science means, it doesn't change, right? And for the most part, the law shows that we just don't have a whole lot of loss. We don't have enough loss to really concern ourselves with, but we do have loss. And some of that loss comes from this, and how we combat it is with, steps that we're going to talk about in a minute. But, excuse me, when we coil that wire up, even if we mash them close together, the orientation of our magnetic field is still going to, it's going to want to go around the individual wire that particular electron is traveling through. So your magnetic field, each magnetic field is going to overlap, and it's going to create this overall magnetic field like so. But at the same time, you've got little bitty magnetic fields that are going around the wire, each individual one. That's what we refer to as eddy currents. Okay? So you ever stood on the bank of a creek or a river with flowing water and there's a stick sticking in the water? What happens to the water as it travels downstream? Okay, it might fork a little bit and it might spin just a little bit, right? That's an eddy current. And that's exactly what's happening here, is we've got eddy currents. So how we can combat the eddy currents and make the transformers more efficient is to take and put a piece of ferromagnetic material inside of it. So the reason that thing is heavy as it is because you've got ferromagnetic material inside of it. If you flip that whole thing over, if you could flip it over, the bottom is sealed, but if you could flip it over and see on the bottom, those coils are sticking out of the bottom too. Okay, so they're going around ferromagnetic material that's actually laminated, kind of like a piece of plywood. And those two steps, putting a ferromagnetic piece of material to give those eddy currents and magnetic fields that we're losing a place to go, further limits that loss. Okay? So what we have here is an electromagnet. Is all it is. That's all that thing is an electromagnet with another coil of wire next to it. This is what picks up cars. Strong enough magnetic field that you can pick up a car with. Okay? So we create ridiculously strong magnetic fields with these things. Again, the doors are held open in the hospital by electromagnets. Fire alarm goes off. They don't want the fire to spread, so they shut the doors. Whole lot more efficient just to turn off all electromagnets. They're solenoids. A solenoid is an electromagnetic magnet without the core. Flip a switch, turn all those off, and the door's shut. Instead of having people run around the hospital shutting the doors. Right? So we take a solenoid, we stick a metal core inside of it, and we can create an electromagnet. If we stick another setup exactly like it on the opposite side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. And we'll send that on down the line. Then if we have the exact same number of turns on, this is always going to be primary side. Primary side is always going to be the side that you supply the electricity to. Okay. Secondary side is the side where we induce the current. Okay. So primary side and secondary side. So if I supply electricity to the primary side of this setup, I'm going to create a magnetic field. Changing magnetic field because I'm using alternating current, right? It goes in one direction, it goes in the opposite direction. If I move another coil of wire over close to it, then I'm going to create electricity in a magnetic field that we're not going to use, but create electricity in the secondary side. And the amount of electricity we create in the secondary side is going to be directly proportional. All right, what does that mean?
It means if one goes up, the other.
One goes up, the other goes up. Directly proportional to the turns ratio between the primary and secondary side. That's what we refer to as transformer law. So if you look, we've got two of them, really, two transformer laws, one for voltage and one for intensity. Excuse me, the transformer law for voltage turns ratio is a direct relationship. Okay, so what do you see there? In page 89, you see voltage, V is voltage. Voltage on the secondary side over voltage on the primary side is equal to N here represents a number of turns. So number of turns on the secondary side over number of turns on the primary side. All right. So voltage on the secondary side over voltage on the primary side is equal to number of turns on the secondary side over number of turns on the primary side. Right? So when you can simplify, right? Simplify your the formula. So voltage on the secondary side, we don't know what it's going to be. So we're going to say that's X. All right, so that's our formula. X over voltage on the primary side. Let's say we give this 1 volt. Okay, is equal to number of turns on the secondary side. What we've got here is 1, 2, 3, 4, 5, 6, 7. Let's simplify that. Primary side looks like that. Secondary side looks like that. What's the turns ratio? 1 to 1, right? So we've got number of turns on secondary side is 1, number of turns on primary side is 1. Cross multiply, we have 1x equals 1. Divide both sides by 1, and then we have x is equal to 1. Mathematically. A true statement. It is. All right. So now then, let's do this. What do you suppose happens there? If it's directly proportional to the turns ratio, now our turns ratio is 1 to 2. We feed this 1 volt. How much should I have over here? 2 volts. 2 volts. I feed this 1 volt and I have 3 over there. What should my voltage be? 3. Right? It's directly proportional. The more you have, the more you have. Right? So this is the basis for your step-up transformer, which what's been coming around is the step-down transformer. Okay? The step-down transformer, it goes in the opposite direction. The step-down transformer, what you have is intensity on the primary side over intensity on the secondary side is equal to the number of turns on the secondary side over the number of turns on the primary side. So if we're looking at a step-down transformer, what we want to do is step down our voltage, and what we get in return is a step up in amperage. Okay, so if we have, we feed, let's say, 1 amp to, let's go back to this, we feed 1 amp to this, then what's our amperage going to be on the opposite side? It's inversely proportional. We have 1 amp here. What's our amperage going to be now? It's going to be half. Right. So it goes down by a factor of 2. Divide in our, 1 over, or let's see. Yeah, 1 over x is equal to secondary side 2 over 1. Again, cross multiply, we'd have 1 equals 2x. Divide both sides by 2. X is equal to 0.5. And the same thing as 1/2. So as voltage goes up, amperage goes down. Okay. So this, though, our step-down transformer, doesn't step down intensity. It doesn't step down amperage. What we feed into our high voltage transformer, or the construction of our high voltage transformer, is that we have a set number of turns on the primary side. Secondary side, we have a ton of turns. Okay, so if I feed this, 100 volts, and my turns ratio is 1 to 1,000, it's directly proportional. How much is my voltage going to be on the secondary side? 100,000. Okay, now I can make a chest X-ray. I can shoot pretty much anything that you got, right? If I feed this side 50 volts and my turns ratio is 1 to 1,000, how much am I going to get on the other side? 50,000. Step up. Step up is always voltage. Well, in both cases, they're always voltage. With the transformers, always voltage. Step up means you're stepping up our voltage. The step down, you're stepping down voltage.
So step down's always a factor of 2.
Not necessarily. Not necessarily. So the filament current, the current that's going through the filament before we make an exposure is about 25 volts. Okay, so if we had 250 volts going through our primary side, then it'd be a 10 to 1. Yeah, I just use that for an example. Yeah. Okay.
So then the step up, you said it was thyroid, and the step down
Is
inverse.
inverse. And wait. No. Back up. In both cases, the voltage is direct. The amperage in both cases is inverse. Okay. So voltage in both the filament transformer and the step up transformer, the voltage is directly proportional to the turns ratio. Now, where you might have gotten inverse is that the filament transformers turn around. So our filament transformer would have more turns on the primary side than what we have on the secondary side. The purpose for that is to take our maybe 250 volts and drop it down to 25 volts. Why do we only want 25 volts on the filament? So it doesn't burn up. That's one. Main reason is we don't want. I passed around an X-ray tube, right? Or was it just a Crookes tube I passed around? Have I brought you an X-ray tube, a full X-ray tube? Okay, the distance, and I know it draw pretty big up here, but the distance between the cathode and the anode on the X-ray tube is only about that far. It's very close, right? So what you don't want is to feed it 250 volts because you might have, or 240 volts as it were, you might have electrons jump across before you're ready for them to go. Okay, so to heat the filament, what we want is very low voltage so they don't make that travel across the tube until we hit it with high voltage. Okay, so the purpose for the filament transformer is to make sure that doesn't happen, is to reduce the voltage. Remember V equals IR. If we, again, you notice that one coil was skinnier than the other, right? So if one coil is skinnier than the other, what does that do with resistance? It increases resistance, right? So with the whole gamut of everything that we talked about so far, and where was I going with this? I forget where I was going to tie all that in. Maybe it'll come back. What's that?
Well, we were talking about the amperage versus the direct, all that stuff.
Yeah. Maybe that's.
Sorry,
I don't
trying to
know.
tell you something.
I don't know. Well, I appreciate you trying to help. Sometimes a crazy train just leaves tracks. But with the oh shoot, I forget.
So voltage is always direct, amperage is indirect.
Correct.
Is that kind of the basis that we need to know?
Yeah. And I think that there are a couple of, if you've got your DeAngelis, I think there's a couple of questions that are straight out of the DeAngelis on working the transformer law. So if you don't have DeAngelis, you might want to get one or get with somebody, and kind of look over the DeAngelis questions on that. Okay, so we still have a lot of loss going on here. All right, so we fixed as much as we could the loss in the primary side, right? We gave it a laminated core. Laminated core, very key to making sure we get rid of as much as of the eddy currents as possible. It helps reduce the loss and the changing of the current back and forth. Hysteresis is what they refer to that as. But what do we have over here? We got eddy currents because we don't have a core, right? So in order to reduce the loss on the secondary side, again, we're going to put a core in it. It's just that in my drawing here, I'm going to make it skinny. Now, what we've got is in relationship to each other, these two are kind of flipping back and forth. Okay. So where is the electricity going down here? Where's the electricity? Not the electricity, the magnetic field. Let's say this south end is coming out and it's going this way, is it not? And it's way out here trying to reach back in. Is there a way that we could take and draw those magnetic field lines in together so that they join each other at top and bottom? Let's Is there a pathway that we could create between these and those? Give you a hint. Look on page 90. Join them together, right? So if I join them together like this, maybe we don't really catch all of these, but the ones that might be trying to get out past that coil wire, are they more likely to go directly down that pathway right there instead?
Yes.
Answer yeah. So it further reduces loss. All right, so this is what we refer to as an open core transformer. Open core transformer basically means we got two completely separate electromagnets. One we energize and the other we induce an electric current through, right? So this one we energize, we provide with alternating current. We've got metal cores in them, so they're efficient, but they aren't as efficient as they could be. If we join them together, if that was open core, then when we join them together, we create closed core, right? So that redirects some of those magnetic field lines to just go through these two cores. But we still have a problem. We're still losing these. Those over there. Yeah, we are. We are. So what if then, instead of using open core or closed core, we took the two and we stuck them on top of each other? I gotta draw this just right or I mess up the pins. Yeah. What if we took, we got a cool wire. I thought it wrote better than that.
Right on, right here.
Yes, thank you.
Yes. I'm second up here today.
I lay stuff down all the time. And forget where I put it. This guy thing. Alright, so what if I had a coil wire and then I put that coil wire into, you know what a cinder block is? Mm-hmm. Okay. Haydite block is what some people call it. It's a cement block. It's a rough cement block. But what it is you've got this big block and then you've got this brace in the middle of it, right? So the whole thing is, most of the thing is hollow, but it's got a kind of a brace in the center of it so that you can, put stuff on it. So imagine one of those, but it's made out of laminated steel. And you wrap your coil wire around the center of that, and it comes out like that. And then you got a big hole here, but it also goes that way. You got a big hole here. It just lightens it, is all it does. But you're also joined together there and there. And I told you all more of a Picasso than a Rembrandt. And there, and there. Okay, so let's say I feed that electricity. Okay, so that's a hole. I did so good until I got to my E. I was proud of myself, and then let's try it again. Let's even make it more complicated. That it looks like a P, but you get the idea, right? So you got this thing that's solid. You got this thing that's solid, right? Now, where can the magnetic field go? Do we have a pathway to take the magnetic field that's coming out and make it all go back right through the middle of that coil? Yeah. Now, what if we took and we stuck a second coil of wire on that? Well, it was a smaller coil of wire, thinner wire. There was more of them. I stacked them right on top of each other. We create magnetic field off of the red one, right? And all those magnetic field lines are going through, this entire thing. This is what we call a shell type transformer. So we take all those magnetic field lines and we're jamming them right back up through the center of this thing. We wrap it with a secondary coil of wire with many more turns. Where's the magnetic field going? Back to itself. Back straight through that secondary coil. So in a shell type, what we're doing is we're giving the magnetic field lines more of a, it's not really 360 degree, but it's at least redirecting those magnetic field lines as much as it can straight back up through the center of both of the coils of wire. And in so you increase the efficiency, reduce the loss. Most efficient type of transformer shell type. We're just going to leave it at that. I'm not going to overcomplicate it. We're going to talk about different, they call it generators, but we're going to talk about different types of transformers again later on. Okay, so what's the takeaway from all this? Well, we can create a magnetic field with electricity, right? And with electricity, we can create a magnetic field. We can increase that magnetic field using Faraday's law, right? We can induce electric flow in a secondary coil, again using Faraday's law and the induced magnetic field. We can increase or decrease our voltage and amperage dependent on the turns ratio between the primary side and the secondary side. If the number of turns goes up on the secondary side, what happens to our voltage? It goes up in direct proportion to the primary side. Turns ratio on the primary side versus secondary side. Double on the secondary side, double your voltage. 10 times on the secondary side, 10 times the voltage. 1,000 times on the secondary side, 1,000 times the voltage, right? So voltage is directly proportional to the turns ratio between the primary and secondary side, but amperage intensity is inversely proportional, right? So the more turns on the secondary side, what's going to happen with your amperage? It's going to go down. It's going to go down. Right. I still can't remember exactly where I was going with that.
Turns ratio on the primary side, right?
Turns ratio on the primary side
For direct, for voltage.
For voltage, the turns ratio on the secondary side is higher than the turns ratio on the primary side, voltage goes up. On amperage, if the turns ratio is greater on the secondary side than on the primary side, amperage goes down. Yeah. Okay. Is there recording. I'm on this thing. We're right at whatever. Oh. It's not the only place that we see induction. All right. This is what we refer to as an induction motor. Okay. I pass this around. It's kind of dirty. It was actually out of a washing machine. This is not what we use in the X-ray tube. The one we use in the X-ray tube is just a little harder to define. I'll show it to you eventually. But this is an induction motor. And the way an induction motor works is basically the same way, except for you're not creating electricity on any secondary side. The way an induction motor works is that it works kind of like individual little electromagnets. So now imagine I've drawn the X-ray tube, as if you're looking at it from the side. Imagine if you're looking at it from the end. So what you've got is you've got the big portion of the X-ray tube, where the anode end is, right? That stem that it rotates on, it sticks out. Okay, that's what we're looking at here. Okay, so the anode is inside of here, the target area is inside of here. You're looking down onto the stem end of this thing. An induction motor is outside of the X-ray tube. We still consider it part of the X-ray tube, but it's not. And it's not inside the tube, but we still consider it part of the X-ray tube. The induction motor is like this in that you've got one wire, right? And the one wire, or one collection of wires, they're all interconnected. Each one of these are connected to each other, but they all work independently. Okay. So if I send electricity through this, let's say I send it through it and the electricity is going in that direction, it's going to take a little bit of time for the electricity to get to this coil of wire versus if I plug it in right here. Well, let's go with this. Here's the wire. Plug it in right here. It's going to take a little bit of time before it gets there, right? So if I can control how quickly it gets to each one of these, then what I can do is I can fire those off in a specific sequence. And our induction motor on our X-ray tube, let's say it only has 4 electromagnets. It does not. It has more than that. But let's say we've got a piece of ferromagnetic material inside of that rotor. And let's say I fire that magnet up. Where is that piece of ferromagnetic material going to try to align? Yeah, it's going to travel that way, right? So it turns off and now it's right there. But what you'll notice whenever I do get an X-ray tube to you is that they are very well balanced. You ever try to pour a bug out of your whatever drink at a cookout or whatever. You turn your glass and what happens to what's inside of the glass? So it just the bug doesn't move, right? So you got to pour it towards you, or you got to accommodate the bug. So where I was going with that was the X-ray tube is very, very well balanced, and whenever you hold it, you turn it, and it's so well balanced that the rotor doesn't turn hardly. It barely moves. All right. So let's say that my ferromagnetic material gets there and I turn it off and I fire that one up. What's going to happen? It's going to go. It's going to keep going. Turn that one off and I turn that one on, and same thing happens. So that if I fire those in the right sequence, then I can take my rotor and go from 0 to 3,600, maybe let's just say 3,000 to make it easy, RPM in 1 second. Okay. Anytime you introduce mechanical energy into something, it makes it more costly to run, right? But if we can use electricity to power this thing to rotate that rotor, then we can rotate it very efficiently. I'm an old school car guy. I like a gas engine. I like the sound of it. And it just hurts my heart that almost any Tesla would outrun, most cars on the road. But it's efficient. because of that. You know, you don't have the internal combustion, you don't have all the moving parts that you have. We can rotate that from 0 to 3,000 RPM in 1 second. You press the prep button, and that's what happens. You start heating that filament up, but that thing starts to turn so that these things fire in a specific sequence so that you get from 0 to 3,600 RPM, starts at miles an hour, RPM in 1 second. It doesn't take long. It's really, really quick. Okay, but have you ever noticed that whenever you make your exposure, I already said that this thing is really well balanced. You know, I mean, if you were to take it, you know, take the glass off of it and spin it by hand, it would spin for a very, very long time. Is your X-ray tube, your rotor spin for a long time after you make exposure? It's usually maybe 5 seconds, at most 1 minute. You know, if it's really hot, it may spin for about a minute, but it's usually done within 5 seconds. What happens is after you make your exposure, the electromagnets fire in a reverse sequence to stop your rotor. Now, why would we want to do that? Wear it down, exactly. So they have to turn, and they have to turn on something. So we'll get into this a little bit later on, but they have to turn on something, and the more it turns, the longer it turns, the more it wears out the bearings, and the quicker your X-ray tube, you know, the life of your X-ray tube is going to be over. So why is that? It's friction. What's friction cause? Heat. What's the main thing that kills X-ray tube? Heat. Right. So now we've got two different places that, you know, heat becomes an issue. The bearings, and we're going to talk more about this, the bearings and also the heat that we create on the filament and we deposit on the rotor. Okay. Induction mode. 0 to really fast in 1 second. It spins backwards to kill it, but it works off of electromagnetic induction. We use electricity to create electromagnets to drag a magnetic field around and around and around to turn a rotor. Okay, so just real quickly, and then we're going to be done. This is going to be a wrap up. So it causes this whole section. Electromagnetic devices. There are three that you kind of need to keep in mind. One is an induction motor. You know, the auto transformer works off the same laws as a transformer. Number of turns primary side versus number of turns on secondary side, same thing. So step up transformer, step down transformer, the filament adjustment, all of that works in the KVP adjustment. All of that works off the same transformer model. Again, we'll talk about it more later on. Also, electromechanical device. This is truly electromechanical. But another thing that every system has, your house has as well, as protection, is an electromagnetic device. Is a thing that, let's say you plug in too many things in your house. Right? You plug in too many things. You got your toaster going, you got your microwave going, you're cooking something in the oven. Because it's hot in the kitchen, you turn a couple of fans on. What happens? Circuit breaker. Yeah, circuit breaker. Just for safety. If something happens, our lab is bad about this. Every time a storm blows through, if you look at as you enter the lab, far back right hand side is where the transformer generator is. That whole electric cabinet, and there's a circuit breaker on the wall there. So if you ever go into the lab and nothing turns on, it's tripped. You're gonna have to snap it down, snap it back up. And it's just fire safety. You know, you're dealing with a lot of electricity. Electricity can be dangerous, as we saw in the car videos. The car's caught on fire. It can be dangerous, not in exactly that same way, but you can have electrical fires. Circuit breakers and fuses are both devices that kind of prevent that. I think that might be on this, so I want to make sure to talk about it.
And fusers?
Fuses, yeah, fuse. You don't see them a whole lot anymore, but you see them in your car. You get into a fuse box, and then your car, what you have is just these two little posts that come up, and you got a plastic thing, and you've got a little piece that combines, they join together. You that does the same thing as a fuse box. The only thing here is that instead of flipping a breaker, it burns it out.
Is that another safety mechanism?
Yeah, it works the same way as a circuit breaker. Yeah, you know, whatever component of electricity gets too high, it burns it out, trips the circuit breaker, kills electricity. Okay. Any questions? I worked up a sweat on that one. Any questions? All right, well, if you think some, we'll have time on Wednesday to talk about it before we get into the next section.